Swayam Prabha. Digital India. Educated India.
Okay, welcome back. So, before we begin the next session, let me remind you that we have basically discussed the general aspects of manufacturing automation. We have discussed what are the benefits of the automation, why we need the automation particularly in India for example, and we convinced that it will create the new and more interesting jobs than the normal routine works in the mass production. Then we have discussed some of the strategies which are required for manufacturing automation, so that the production capability, production capacity or production rate can be enhanced. Then we discussed some of the aspects of the part transfer. We said that there could be inline flow or the rotary flow, and we have accordingly the rotary indexing machines or the inline machines which can be used in the flow line automation. So, next we discussed about the flow line automation, which we said that it consists of the series of either processing or assembly or sortation or inspection machines which are connected or integrated by the material handling devices. Now, the automated flow lines can be analyzed based on the average production rate, as we said, based on the line efficiency and the cost per item produced on the line. These are the things that we discussed last time. So, we said that the line efficiency is important because this will dictate us, or this will show us what is the proportion of time the line is operating. Okay. The rest of the time the line is down, and why the line becomes down, that we will discuss now. Well, to analyze the automated flow lines, let us assume a synchronous transfer system with an ideal or theoretical cycle time Tc. What is synchronous transfer system? I will remind you that it can be the inline or the rotary indexing, where the parts or the sub assemblies are being transferred and then they stay for some times for the processing to be over. Cycle time, what is the cycle time? This is the time taken for the processing. Either it can be a machining process, it can be a metal forming process, or it can be an assembly process. So, the entire task to finish, including the transfer of the parts, that is the actually ideal cycle time. Okay. Now, the Tc, which is the cycle time, as we said, this is the time required for parts to transfer plus processing time at the longest workstation. Now, what does it mean? In a flow line, we have different machines, and all these machines may require different processing time. Some machine may require 4 minutes, for example, another adjoining machine may require 4.5 minutes of processing time, another machine adjoining to other side may need 3.5 minutes of processing time. So, the longest one, which is maybe 5 minutes or 4.5 minutes, that has to be considered, because then only all the machines would be covered, and in that case what happens, that the machine which takes less processing time, they have to wait for some times for the parts to get transferred. Let us see how it is done. The stations requiring less processing time than the longest station will have a certain amount of idle time. Okay. Now, what is that? Let us say we have here we have the time. Okay. So, this is the time, and we will find out what is the cycle time. So, this is the cycle time, let us say this much, this is Tc. Okay. Tc is the cycle time, as we said, that is required for parts to transfer plus processing time at the longest workstation. Okay. Now, in this we have, let us say, this much is the time which is taken for transferring the parts, and this is the time which is taken for the processing time for the longest workstation. That means, the processing time for the machine which will take the longest processing time. Now, those machines which will need less time than the longest processing time, it needs some idle time. So, this is the idle time. Okay. This is the transfer time, and this is the processing time. Okay. This is the processing time. So, what is happening is that whole thing is the cycle time, Tc is the cycle time, and this cycle time includes the transfer time and the processing time, and within the processing time, those machines which will be slower, they need some idle time. So, that is the idle time that we have. Now, this Tc cycle time, this we call as the ideal cycle time. Okay. This is the ideal one. Ideal one means that this can be achieved if everything goes okay. If there is no downtime, no machine breakdown happens, then that Tc is the ideal cycle time. In fact, what as in practice happens is that there could be some sort of machine breakdown in a cycle or in few cycles. So, in that case, if this is the time, okay, and if this is the Tc, let us say, and here we have the transfer time, okay, here we have the processing time, let us say, and this is the idle time. But there would be certain breakdown in the machine, in the line. So, let us say this is the machine breakdown. Okay. So, this machine breakdown, let us say, we will say, some actual production time. So, this Tp we will say as the actual average production time. So, actual average production time, that means will be more than the ideal cycle time by the time it takes for taking care of the line breakdown. Okay. Now, let us say that we have Td is the average downtime to diagnose the problem and make repairs when a breakdown occurs. What we mean is that in the line, when the line is working, certain breakdown happens, and for that breakdown there should be some operator or some technician who will take care of, diagnose it and then correct it to rerun the machine, and let us say that takes this much of time. How to find out that time? Let us say f is the frequency with which the line stops per cycle. Let us say the line stops per cycle once in every 100 cycles. So, if 1 in 100 cycles, so 1 by 100 is the frequency. So, this is 0.01. Okay. So, let us say this is the f, which is the frequency with which the line stops per cycle. Let us say once in 100 cycles, or it may be once in 10 cycles, once in 1000 cycles, that depends, and on which factors it will depend we will discuss later. Now, Td is the average downtime to diagnose the problem and make repair when a breakdown occurs, and the f is the frequency with which the line stops per cycle. So, this is actually the f into T and the D. Okay. So, the Tc, that is Tp is the actual average production time. This will be more than the ideal cycle time by the factor f into Td. Okay. So, we can write that the Tp is equal to Tc plus f into Td, and this is the factor which actually counts the line breakdown because of various reasons. Okay. If the machine stops, or if something went in the machine, or the tool is broken, or something. So, this takes, let us say, Td time, and the frequency is f. So, f into Td is the time, and therefore, the actual or the average production time will be more than the ideal cycle time by this Td into f. Now, once we have the average production time, 1 upon time is the rate, production rate, 1 upon production time. So, therefore, the average production rate, which is RP, this will be 1 upon Tp, and Tp we found out by the ideal cycle time and the Td into F. Here you mind one thing, that this can be found out because we know that how much time it takes to process a part. Let us say to machine a part or to assemble a sub assembly, we know the Tc, which is ideal. Then from the experience of the line performance, we will be knowing that normally on an average how many breakdowns happen in how many cycles. Let us say 1 breakdown in 100 cycles on an average, so on. So, we know the F, all right. If we know the F and we know that how much time it takes on an average again to repair and to rerun the machine, then F into Td, if we add to Tc, we can find out the actual or the average production time, and this average production time is the actual production time, whereas this Tc, if you see, okay, this is the ideal one, in the sense that if everything goes okay, if nothing happens and the line is running perfectly well, then the Tc is the cycle time, but it does not happen. I mean, most of the time there is something or other because of which that F into Td has to be taken care of. So, average production rate we can find out if we know the Tp, because 1 upon Tp will be the average production rate. Once we know the average production rate, then the theoretical production rate will be 1 upon Tc. Okay. Tc is the ideal cycle time. So, this is the theoretical production rate, meaning that if nothing happens, once again this much production rate will be getting. But since we have that F into Td, so therefore, the line efficiency we can find out by dividing the Tc and the Tp, and the Tp we found out Tp is equal to Tc plus F into Td. So, therefore, this actually is Tc divided by Tp, and the Tp, as we said, is the average production time. So, the average production time, this is the ratio of the ideal cycle time and the average production time. So, this is equal to Tc divided by Tc plus Ftd, because this Tp is equal to Tc plus Ftd, that we have seen here, okay. Tp equal to Tc plus Ftd. So, therefore, we know the theoretical production rate, we know the line efficiency, and then proportion of downtime means that for how much the line is down. Here we are not calling the machine, because a line consists of several machines, they are integrated, okay, and they are integrated with the material handling device. So, therefore, the proportion of downtime of the line, this is given by the F into Td, the time the line is down, divided by the actual average time Tp. Okay. So, this will actually be F into Td divided by Tp is equal to Tc plus Ftd, all right. So, this way we can find out that for how much time the machine is down, the line is down. If we know that, then we can find out that in general we can check that E plus D should be equal to 1. If we see that Tc divided by Tc plus Ftd and plus Ftd divided by Fc plus Ftd, this is equal to 1. Okay. So, this is a check. So, we know that how much time the machine is up, efficiency, and how much time the machine is down. Next, let us see what is the cost, how to find out the cost per item produced in the automated flow line. Let us say that Cm is the cost of raw material per product. Suppose we are discussing the machining or production of the particular part. So, Cm is the blank, the cost of the blank, cost of the raw material per product. Cl is the cost per minute to operate the line, including labor, overhead, maintenance, and the allocation of capital cost of the equipment over its expected service life. Let me explain it to you. What is it? Cl, this will include that how much money we are spending per minute to operate the line. How to find out that? We have installed the line, we have certain costs which have been incurred, and let us say it is given that the life of the line will be, let us say, 10 years. Okay. So, we can find out what will be the cost per minute, because we have overall cost for installing the line and the line life is 10 years. So, that is one thing. This is the cost per minute to operate the line. Now, this will include also the labor, how much you are paying for the operators, if there is any of the other maintenance people which are involved in that. Overhead. Overhead is something which we pay for to run the line. For example, the line is under the roof, that is a building, that building has some cost. We have the electricity, for that we need the investment. We have the hydraulics, pneumatic lines, we have the disposal of the chips, okay, which and so on. So, everything included in that overhead. Maintenance, if the line anything happens in the line, in that case it has to be repaired, it has to rerun. So, that maintenance charge has to be included here, and the allocation of capital cost of the equipment over its expected service life. Okay. So, this is like how much we have spent, as I explained it to you earlier, how much you have spent and how much time we require for that particular operation for which we are finding out the cost. Okay. Now, all these things will be included in the CL, which is the cost per minute and overhead and the capital investment. CT is the cost of any disposable tooling on a per workpiece basis. So, during the operation we will have some fixtures, and those fixtures will be required for particularly machining or assembling the parts. So, this cost is the CT. So, therefore, the cost per workpiece will be equal to CM plus CL into TP, because CL is the cost per minute. So, that has to be multiplied by the TP, which is TP we have found out. Okay. This is the TP, which is TC plus TD into F, and that will give you the CL into TP plus the cost of any disposable tooling, which is the CT. So, this all together CM plus CL into TP plus CT will give you the cost per workpiece. So, this is easy to find out that how much will be the cost per assembly or per piece which is being machined on the line. So, as you understand that this is different than what we have done in the case of finding out the cost of the cost of an workpiece which is being manufactured in a standalone machine, because in the standalone machine we do not need many of these things, but we need something else. So, those are to be included. So, therefore, in this case this is the cost per workpiece when it is being done on the automated flow line particularly. Let us discuss next topic, that is the partial automation. What is the partial automation? Meaning, in the beginning, if you remember, I told you that automation actually begins where the mass production leaves off. So, that means that automation cannot come overnight. It is a gradual process, and it is we call as the evolution. Okay. Evolution. See, there are two words, one is the revolution and another is the evolution. So, this is an evolution because it does not happen overnight, and we are not throwing out all the positive aspects of the mass production. So, therefore, initially we cannot overall install the automation, but it will be partial automation. That means, there will be some manual operations in the process. Now, there are two basic reasons why the partial automation should be introduced. First is the mechanization of a manually operated flow line is often introduced gradually, as I said just now. And the second reason is some manual operations are difficult to automate, I actually told you earlier also, and it may be uneconomical to do so. For example, alignments, assembly, inspection, etc. Let us give you an example. Suppose there are elements of bearing, okay, let us say cylindrical bearing, and those elements, each of these elements have to be tested for any scratch or any defect, all right. So, there are millions of them in the production of the bearing, and if we have to have a machine, automatic machine with some sensors for checking each of these elements for any kind of crack or any kind of small scratch, this will actually take a very sophisticated machine and it will be very expensive, whereas the human being can do it much faster and it in a much easier way and more accurate way probably. So, that is the reason where we actually introduce some manual operations in the automation, and this is called the partial automation therefore. So, in the partial automation what happens? The total line cost, this will be given by another formula rather than this CPC equal to Cm plus CLTP plus Ct. See, mind it that this is the formula what we are using for finding out the cost in the automated flow line, where we have the complete automation, all right, and this is the one that we are talking about, that where we have still some manual operation or manual machines. Now, here the total line cost will be equal to N0 C0 plus Na into Cas plus Cat, all right. Now, N0, this is the number of manually operated stations, okay. It could be any number. This is multiplied by the C0, and C0 is the operator cost per manual station, how much you are paying to the operator for operating the manual station, plus Na into Cas. Na is the number of automatic stations and Cas accordingly is the cost per automatic workstations, which will be rupees per minute. These two plus Cat, this is the cost per minute of the automatic transfer mechanism, which will be used for both manual and automatic stations. So, therefore, you can see that Cat is not multiplied by neither NO, N0 nor NAS, because this is the cost per minute of the automatic transfer machine or automatic transfer mechanism, which is the material handling device. So, this automatic transfer mechanism, it is, since it is used for both NA and the NO, that is the manual stations and the automatic stations. So, therefore, this will be overall plus Cat. So, that is how we can get the total line cost, which is equal to the multiplication of the manual operations and the cost plus automatic operation and the cost plus separately the cost per minute of the transfer mechanism. Now, of course, N0 plus Na, that will be the total number of machines or workstations on the line. This is understood. Okay. So, therefore, the average production time, this will be again the ideal cycle time and the average downtime per cycle, which we said as the F into Td. Okay. Ideal cycle time plus average downtime per cycle, we said Td into F, that we are writing as Na into P into Td. Na, we have seen that this is the number of automatic workstations in the line. Small p, this is the probability of part jamming at a particular station. See, since these are the automatic machines, so those machines can have the breakdown by jamming the parts. Okay. The parts may jam into the automatic workstation, whereas it may not happen in the manual workstations. Okay. So, therefore, this has to be considered, that what is the probability of part jamming at a particular station, and that has to be multiplied by the number of automatic workstations and of course, the Td remaining. So, the F is equal to now the probability and the Td. Okay. So, this will be probability into Td and the number of this thing. So, this will be F into Td, that we are writing, the same thing here. Okay. Now, as I said that this is to be noted that the breakdown occurs at automatic workstations only, and therefore, it is only the Na here that is considered. So, let us look into the next topic, which will be the production and the throughput. I will give you the overview of the production and the throughput, what it is, and the details we will discuss in the next class. See, like production and throughput, production time, we know the production rate, we have seen that production rate is 1 upon the production time, all right. Now, the automatic assembly machine, whether it is inline or rotary, produces a complete assembly every time it indexes. This is very important to understand. That is how in the first lecture I told that 10 seconds was the time taken by Henry Ford to get one car. That means, each 10 seconds it indexes one car is coming out. It does not mean, by the way, that the whole car is made by 10 seconds for 10 seconds, please. So, there is an indexing machine, the assembly is made in different workstations. So, once it is indexing, at the final stage one full complete product is coming out. Okay. Regardless of the number of stations, there could be 100 workstations or 200 workstations, every time it indexes you get one complete assembly or a complete product. Therefore, to compute the production rate of an automatic assembly machine, one needs to know only the indexing cycle time. The number of stations is immaterial. All right. Now, what is throughput time is the time required to complete an assembly from start to finish. So, therefore, the throughput time will be always more than the production time. Okay. How much more we will see in the next class. Thank you.